Let's try to discuss this question here. A point charge Q1 is equals to positive 2.4 microcoulomb is held stationary at the origin. So now Q1 is placed at origin. A second point charge Q2, which is negatively charged, negative 4.3 microcoulomb, moves from point X, which is X is equal to 0.5, Y is equal to 0, to point X is equal to 0.25, Y is equal to 0.25. Okay, so that's a lot of information. Let's try to draw it on this paper over here. Okay, I will put an initial situation and also a final situation because I think there's charges moving from one place to another, right? So I'll put an initial and final. Then because I know that they are going to use Cartesian coordinate x and y, so I'm going to build a xy coordinate over here. Okay, so this is my xy coordinate. Okay, then they mentioned that Q1 is held stationary at the origin, so that's a situation initially. So let's put a big red positive charge at the origin. Okay, so Q1 is equals to positive 2.40 microcoulomb. Okay, a second point charge Q2, which is negative 4.30 microcoulomb, moves from point X is equal to 0.215, Y is equal to 0. So initially it was at this coordinate over here. So initially, where is it? X is equals to 0.15, so means that there's a bit of distance in between them. So this is Q2, negative 4.30 microcoulomb. So we know that the X coordinate is 0.15 positive, so it's to the right. Okay, X is positive 0.15, so it's 0.15 to the right. Let's label it. So this one, the distance here is 0.15 meter. Okay, and the Y coordinate is 0, so the Y, there's no changes in Y. Initially, it was at the origin, X is equal to 0, Y is equal to 0. So Y is equal to 0. Then Q2 is also at Y is equal to 0. So they are on the same height. Okay, I'm not supposed to use the word initially. Okay, what I'm trying to say here is that Q1 and Q2, they are at Y is equal to 0. So you see them to be on the same height. Okay, then now Q2 is going to be moved from this position here to another position, which is X is equal to 0.25, Y is equal to 0.25. Okay, so they didn't mention Q1 being moved, so I believe Q1 will still remain at the origin. So Q1 is still at the origin. But what happened is Q2 is being moved to 0.25, 0.25. So 0.25 is definitely further away from 0.15. So let's put it further away. This one is negative 0.25. Go up by another. What am I trying to say? Okay, let me repeat my statement. Because it's positive 0.25, that means it goes to the right by 0.25. Because Y is also positive 0.25, then it goes up by 0.25. So go to the right 0.25. Go upwards 0.25. So you find your Q2 to be around here. Okay, so Q2 will be somewhere around here. So let's label it as Q2 is equals to negative 4.30 microcoulomb. Okay, so initially, never mind, let's label it first. Okay, this one, the distance from here to here, the distance is 0.250, and the distance from here to here, the distance is also 0.250. Okay, so as I mentioned earlier, every pair of charge, you can imagine that there's a spring in between them. If it's a like charges, you can imagine the spring in between them to be initially very long, infinitely long. But now because their distance r apart, it is as if you take a very long spring and compress it to a length r. Okay, but if it's an opposite charge, in this case, it's an opposite charge, because positive and negative, naturally they want to get close to each other. You can think of it as originally they are stick to each other. It's a spring of 0 length. Okay, but now you are trying to pull them apart, so it is as if you take a 0 length spring and stretch it to a final length of r. Okay, so what I'm trying to say here is, in between every pair of charge, you can imagine that there's a spring in between them. So I'm going to label spring in between the two charges, Q1 and Q2. So initially, you can think there's a spring in between them. Then after that, because Q2 moved, then the length of the spring has changed as well. Okay, so initially in between them, there's a U initial. Let's call it as U initial. Initially, the spring stores some amount of energy, but after that, you change the length of the spring. So you can imagine it to be either the spring being stretched more or the spring being compressed less. Okay, so in that case, it will cause a change in the potential energy. So you have a final electric potential energy. Okay, so this is what I'm trying to say here. So there's changes in the electric potential energy. Okay, so now what does the question ask? The question asks how much work is done by the electric force on Q2. So they're interested to know Q2 here experience how much work done by the electric force. Okay, so we know that in between this positive and negative charge, there is attraction between them. Okay, so there's electric force. So that electric force, how much work does it do? How much work does that electric force do on Q2 to move it from this initial position to this final position? How much work is done by that electric force? Okay, so to solve it, it's a standard process actually. We have to first identify whether they ask for work done by electric force or they ask for work done by external force. So in this case, it's stated quite clearly it's work done by electric force. So you can write it as work elect. Okay, so work elect for which charge to move from where to where? For Q2 to move from position initial to position final. So let's just call this point as point initial. Let's call this as point final. So you can say the charge has been moved from initial to final. Okay, we know that work elect, the equation is equal to negative delta or negative change of electric potential energy. So that's work done by electric force, it's standard. If it's work done by external force, then it's positive delta U. If it's work done by electric force, it's work negative delta U. Okay, so you break open the change, the delta. So this will be final minus initial. So it's U final minus U initial. Okay, so feel free to shuffle it around. It's up to you. Okay, you can open up the bracket to become negative UF, positive UI. Okay, that's fine. Okay, so UF here is this spring over here, the potential energy stored in this spring over here. UI here is the potential energy stored in this spring over here. So how do you find how much energy is being stored in this spring over here? Actually, we learned about it in class. Okay, let me modify the diagram a bit. About it in class, if it's 2-point charges, the potential energy will be equals to K, Q1, Q2. Okay, which are the two charges that holds the spring? Okay, you can think of it like that. Divide by the length of the spring, which is R12. But in this case, R12 has changes length, right? So you can say U final. So this is R12 final. Okay, whereas for the initial situation, you can call it as U initial, and this stored Q1, Q2, but now the distance we call it as R12 initial. Okay, so now we can substitute in the correct equation to represent UF and UI. Okay, so negative UF you just put in K, Q1, Q2. You don't need a modulus here because the sign is important. Okay, so this one is R12 final. So plus K, Q1, Q2, R12 initial. Okay, so that's us substituting in the expression for potential energy. Okay, I think there's a lot of things that we can factorize out. So let's do a bit of factorizing. So you can factorize out K, Q1, Q2, all these can be factorized out. So what's left inside the bracket will be 1 over R12 initial. I'm bringing this one to the front because this is positive. This one is negative, so I bring it to the back. So this will be minus R12 final. Okay, so just factorizing out the Q1 and Q2 together with the electrostatic constant. Then after that, what's left here is just a distance inverse being inverse. Okay, so now we are left with substitution, nothing too complicated. So this constant of proportionality, 9 times 10 to the power of negative 8, 9 times 10 to the power of 9 Q1 is positively charged, so positive 2.4 microcoulomb. Substitute in the positive sign as well. Q2 is negative 4.3, so we substitute in negative 4.3 times 10 to the power negative 6. So K Q1 Q2 is substituted in. Then we continue with R over 1 R12 initial. R12 initial is this distance over here. So this distance over here is R12 initial, and the value is 0.150 minus 1 over R12 final. R12 final is this distance over here. This distance over here, we don't have it directly, but we know that it's a right angle triangle with the adjacent and the opposite to be 0.250 meter. Okay, so it's just a simple Pythagoras theorem to be done over here. 0.250 square plus 0.250 square. So what are you finding? You're finding the hypotenuse here. Okay, so if you substituted in everything and you perform the calculation in your calculator carefully, I believe you will end up with the answer, which is negative 0.356 joule. Okay, so that is the work done by the electric force in order to move Q2 from this position initial to this position final. Okay, there's something we can do to roughly check whether our answer has a correct sign or not. So let's try to think about it. Okay, so this one, it's a pair of positive negative charge. Okay, it's a pair of positive negative charge. Okay, so we know that positive negative charge, in between them there's a spring. I'm not saying that there's physically a spring. You can imagine that there's a spring in between them, that initially they want to be as close to each other as possible, right? If you don't disturb them, positive and negative, they will get close to each other. So you can think of it as a spring that is initially very, very short because they are very, very close to each other. So initially zero length. So initially zero length, what does it mean? You stretch more. The more you stretch, then you will store more potential energy. Okay, so let's look at this situation. Initially, the spring was very short. Then finally, the springs gets longer. So if the springs get longer, that means it's stretched more, right? So because it's stretched more, then you will know that they will store more potential energy when you change from initial to final. This process here involves the spring to storing more and more potential energy. So storing more and more potential energy, in other words, means by your change in potential energy is positive. Okay, because from initial to final, there's a gain, so delta U will be positive because it's increase in potential energy. So if you refer to this equation, W elect is equals to negative delta U. If this one is positive, then multiplied by negative, your work elect will be negative. That's why work elect will be negative. So we check whether it matches with our answer or not. Yes, it matches with our answer, the sign. So we think that logically the answer seems to be logical. Okay, that's what we can do. We cannot check whether it's correct or not. Okay, that depends on the calculation. But by doing this kind of simple analysis, thinking about it, whether the potential energy should increase or decrease when the length of the spring gets longer, you think about it, you know whether the potential energy increase or decrease, you can know whether the work done is positive or negative. So from there, you can deduce the sign whether it's correct or not. Then you can say whether the answer is logical or not. Okay, so that's a simple check that we can do. And yeah, I believe that's what I want to explain for this question over here. So thank you very much.